All right, so this is the last of many lessons just delving into understanding complex numbers. And I want to start with a little bit of review, in which if we have a complex number written in Cartesian form, we can write it in Euler or polar form. I'm going to focus on Euler form here. And we've done that many, many times. And keep in mind, visually, we've seen how the real part of a complex number relates to the cosine function, in this case, the cosine of pi over 6 times 6. And the imaginary part of a complex number relates to the sine of, in this case, 6 times pi over 6. And so let's just focus on the cosine part here for a moment. Everything here we've seen before. Well, if we know this is all true, what we can do then is we should be able to go backwards, which means if we see a cosine function, we should be able to imagine it as the real part of some complex number, in this case, z. Or if we see a sine function, we should be able to imagine it as the imaginary part of some complex number. And we can, by doing that, we can utilize some of the properties we've seen of complex numbers in previous lessons. And so first, let's just focus on how we can rewrite a sine or a cosine function as some part of a complex number. For example, here, I have 110 sine times 60t plus pi. Well, this can be rewritten. We can imagine this as being the imaginary part of a complex number, in which 110 is the hypotenuse, is the length of the vector. I'll write this in both polar and Euler form. And the angle is the argument is a 60t plus pi. Or I can write this in Euler form, the imaginary part of 110e to the power of 60t plus pi all times I. And keep in mind, as random as that may seem, it is essentially, just going back here, no difference than once we realize that this is the same as this, and this is the same as this, which we've talked about in previous lessons. If I look at this in reverse, notice the coefficient of 6 here, the modulus of this, is the same number I see there, and the argument is the same value I see there. And so I'm taking these same properties with slightly more complex looking sine or cosine functions, but just applying it logically in reverse. And so similarly, if I see a cosine function, that relates, as we were showing, to the real part of an imaginary number, so I can rewrite this function as the real part of 110 times CIS of the argument, 60t plus pi, or in Euler form, which is what I'll use for the rest of this lesson, 110e to the power of 60t plus pi to the power of I. All right, so keep in mind, before I go on, it's natural to find this kind of abstract, but if I just started with this and asked us to visualize this complex number, but just the real part of it, we would end up having to think about the cosine of this complex number, and we'd end up looking at this. All right, so how do we use this? So let's look at this here. I have two cosine functions that I want to add together. And we may not realize, even though these two functions have a different phase shift and a different amplitude, they behave, if I add them together, as a single sinusoidal function. And so, for example, if I just go to Desmos, this is the graph of 2 cosine x plus 2 plus 5 cosine x plus 3. Notice it behaves like a single sinusoidal function, not a mix of two, which means there must be a way to write this sum as a single sinusoidal function. And we can do so with a bit of algebraic work that gets less daunting the more we practice, and connecting this back to complex numbers. So the first thing I want to do is take each of these and write them as, since they're cosine functions, I want to write them in terms of the real part of an imaginary number. And so for 2 cosine x plus 2, this is what we did in the last question, I can rewrite this as the real part of some complex number in which 2 is my modulus times e to the power of, in this case, x plus 2 being the argument, times I. And I can do something similar with this, 5 cosine of x plus 3, I can write as the real part of 5 times e to the power of x plus 3 times I. And again, thinking back to previous lessons, what would be more familiar is to start here and work your way to here. If we gave you, again, this imaginary number, this complex number of 5e to the power of x plus 3 times I, we'd want a visual, if we just wanted the real part of it, we'd have to, at some point, find 5 times the cosine of x plus 3. All right, so I want to add these two together, which means I want to add these two together, which means, from what we've learned earlier, I can write this as just a single function, the real part of 2 times e to the x plus 2I plus 5 times e to the x plus 3I. And this is what I'm going to focus on now. And next, I want to distribute the I in each of those exponents. In fact, I'll just do that right now to save myself some time. So I'm going to distribute this I, and instead of writing this all out again, through the magic of erasers, I will just write it in. So I have x, helps if I write it correctly, xi plus 2I, and over here I have xi plus 3I. All right, to save myself a bit of time. Next, using exponent laws, I want to realize that this sum I have here, or this sum I have here, I can think of as a product of two exponential expressions. For example, e to the power of xi plus 2I is the same as e to the power of xi times e to the power of 2I. If you just look at it again in reverse, I'm adding two exponential expressions with the same base, which means, multiplying two exponential expressions with the same base, which means I can just add the exponents. And so likewise, I can do that over here. Plus 5e to the xi times e to the 3I. All right. Next, I can take out a common factor of e to the power of xi from both of these. So let's take that out. So e to the power of xi, I'll factor that out of each of these. So what I have left is 2 times e to the 2I plus 5 times e to the 3I. All right, next, everything I see right here, I can write as a single exponential expression. And I can do so really quite quickly with just my GDC. If you just type this exactly as is into your GDC, you'll almost certainly get some complex number in Cartesian form, convert it back into polar form, and you'll get an approximation. So I'll leave several decimals here. It'll still be e to the power of xi here. But again, turning that, using my GDC, into a single approximated Euler form complex number, I should get, and I'll write a fair number of decimals here, 6.309203 times e to the 2.72998. Let's just go 7. It's enough there, times I. So keep in mind, everything I did from highlighted in green took me about 8 seconds, 10 seconds on a GDC. And we've seen before how our GDC can convert these. So now I want to realize that I have these two powers of e. I want to put those back together. And so I want to write this as the real part of, I'll put my coefficient of 6.309 first, times e. And when I put these together, I get xi plus 2.72997i. And if I look in my power here, I have a common factor of I can take out. And once I take that out, I have a pretty familiar form. The real value of 6.309, I'll keep all these decimals for now, to the power of x plus 2.72997 times I. And everything now I see here is a single complex number in Euler form. And I want just the real aspect of it, which means I can now kind of do what we did at the beginning in reverse, which write this as a single cosine function. And this becomes I'll write it to 3 significant figures. 6.31 times the cosine of x plus 2.73. And so notice if I look at my work, I started off with a cosine function for each, turned it into the real part of a complex number, worked with our complex numbers for most of our work, and the last thing I did was convert it back into this cosine form. And so that means, if we've done everything correctly, this sum that I showed you at the beginning graph should behave the same as this single cosine function here. And if I go back to Desmos and just show you the answer, I turned it on, notice they appear the same. And it is rounded, so aside from the rounding, they are the exact same. And so just before I move on to the last question, this work here, which in the notes is summarized by these steps here as well, I do appreciate that it looks daunting. I've tried to break it down to every single step. But it's not so much difficult as it takes a number of steps and it takes a bit of practice. But just practice alone doesn't make something difficult. And so for the last question, same idea, this now coming back to power sources. We have 2 alternating current sources, both at a voltage of 60 hertz. Which means the period is 60 times per second. And I can see one has a maximum voltage of 110 volts, and the other a maximum voltage of 80 volts. And these are the 2 equations. So if we find the sum of these 2, let's determine the single equation, this time a sine function that models that, and therefore what's the maximum voltage of this combined power source. So I will say, when you look at any function modeling voltage, the amplitude of the sinusoidal function is its maximum voltage. So 110 volts there, 80 volts for there. So what we need to do is we need to add these together and find out what's the new amplitude. So let's do that. And this time we're looking at 2 sine functions. So I want to imagine that 110 volt sine function, V1, I'm going to think of that as the imaginary part of 110e to the power of 60t plus pi times I. And V2, I'm going to think of as the imaginary part of 80e to the power of 60t plus pi over 4 times I. And now it's going to be extremely similar to what I did before. The fact we're dealing with the imaginary part won't really make a difference to what we're doing for these next few steps. So I want to add these together. So I get the imaginary part of 110e times, and I'll distribute that I, times 60ti plus pi I plus 80e, and so on. All right, like before, now I want to break up these exponential parts to a product of 2 exponential functions, or 2 exponential expressions. Must be fun just watching me write stuff down. Now I want to take out a common factor, and I can take out a common factor of e to the power of 60ti from both of these. So take out that common factor. All right, now I want to use my GDC to quickly find the sum of this and put it back into a single expression in Euler form. So at this point, I'm approximating. All right, getting there. Now I want to put these two expressions with E back together. And notice I can take out a common factor of I from both of those. So maybe I'll just, from both those powers. So maybe I'll just do that right now. I'm quite tired of writing all this stuff out. So let's get rid of those I's, put brackets around it, put the I right there. And now what I have right here, again, I want just the imaginary part of that. Notice what I have highlighted in yellow is a single complex number in Euler form. If I want just the imaginary part of that, I can imagine this being just the sine of, sorry, not the sine, first 77 point, I'll write it to three significant figures again, 77.8 times the sine of 60t plus 2.33. And again, if you were unsure, and I don't blame anyone for being unsure, on a GDC, I would quickly confirm that we're correct because the graph of this should look the same as the graph of these two sine functions added to each other. And you should be able to check quite quickly. The GDC can't tell you the answer in advance, but once you have an answer, you should be able to check. And like I said, just graph this plus this, and you should see the same graph as just this, and you will. That's it. The question didn't actually ask for a graph or anything. It asked for the maximum voltage, which I said is the amplitude of this. So there's your maximum voltage. So the maximum voltage is approximately 77.8 volts of this combined power source.